Hello everyone, myself Lakshmi from Sri Venkateswara College of Engineering. Today I'll be discussing about theory of computations, in which the topic is turning machines, verifying whether one-tape turning machine run in linear time and verifying time complexity of turning machines. State. We discuss the following family of problems parameterized by integers c greater than or equal to 2 and d greater than or equal to 1. Does a given one-tip Q state turning machine make a most cn plus d steps on the computations on all inputs of length n? For all n, assuming a fixed tape and input alphabet, we show that these problems are co-NP complete and we provide a good lower bounds. These problems can't be solved in OQ of c minus 1 by 4 non-deterministic time by multi-tape turning machines. We also show that the complements of these problems can be solved in big O of Q C plus 2 non-deterministic time and can't be solved in O of Q of C minus 1 by 4 non-deterministic time by multi-tape turning machines. Introduction. One of the goals of researching in the field of computational complexity is to understand computation better. While turning machines are basics model of computation, we can't algorithmically tell even whether a given turning machine halts on an empty input. So we have to ask simpler questions or use a simpler model to analyze. Assume we have a fixed function t n implies r which is greater than 0. A natural question to ask is whether a given turning machine runs in time t of n. That is, does a given turning machine makes a most t of n steps on all computations on inputs of length n for all n. Note that there is no big O notation in this question. The reason for this is a folkloric result that is undecidable even whether a given one-tip turning machine runs in time big O of n. Furthermore, it was proven in 6 that the affirmative mention problem is not decidable for linear functions t. If we allow multi-type turning machines as input, on the other hand, if we restrict the input to one-type turning machines, then for each c, d belongs to n. We get decidable problem. Does a given non-deterministic one-type turning machine run in time cn plus d? We name this problem as halt cn plus d. There exists a different notation of running time for non-deterministic turning machines in the literature. However, in this work, the length of the longest computation on an input is taken as a measure for the time needed to halt on the input. We will also consider problems d halt cn plus d which are analogs of problems halt cn plus d for deterministic one-tape turning machines as input. But while one-tape turning machines can solve the same problem as multi-tape turning machines, they are a bit slower, however, a bit simpler to analyze. It is well known that one can simulate a multi-tape turning machine that is runtime t of n with a one-tape turning machine that runs in time big O of t of n square. And the quadratic slowdown is inherent. On the other hand, a thing that makes the analysis of a one-tape turning machine simpler as crossing sequences. They were first studied in 1960s by Henny, and then who proved the most of the well-known properties of the one-tape linear time deterministic turning machines are they recognize only one regular languages. Harmonics extended this result to one-tape deterministic turning machines that run in time O of n log n. And it was furthermore extended to non-deterministic turning machines by Kobayashi and Tadaki, Yamakami, and Lin. If we would take a different definition of running time of non-deterministic turning machines, such as considering only shortest accepting computations, then linear time one-tape non-deterministic turning machines would be able to accept also non-regular and even NP complete languages. We do not consider such machines if in we can find a summary of results about one-tape linear time turning machines of different types. Methodology. Define the problem. Here, specify the input size n example length of the input string. Clarify what it means to run in linear time. That is, the machine's number of steps should grow proportionally to n. Tape movement count. Here, track how the tape head moves across the input tape. In a linear time turning machine, the tape head should make no more than big O of n moves. State transition. Examine the transition function. The machine should not enter cycles or states that would cause it revisit a tape location more than a constant number of times. Analysis of loops. If the turning machine has loops, for example, when checking multiple characters, verify that they are literally only on a constant number of times for each input character, contributing to the overall big O of n steps. Function count. Here, check the transition table for any functions that are called repeatedly. Each function should complete its task within the most big O of n steps. Simulate the machine. Run the machine on several input strings of increasing sizes. Count the number of transitions and verify that it grows linearly with respect to the input size. Estimate upper bound. Here, determine an upper bound on the number of transitions based on the structure of the turning machine. Ensure that the bound is C into N, where C is an constant. Turning machine basis. A one-tape turning machine uses a single tape and a head to read or write symbols based on the machine's start transaction. Linear time definition. Here, running in linear time means that machine finishes a computation in big O of n steps, where n is the size of the input. One-tape challenge. The machine has to move left or right after each step, making it less efficient than multi-tape machines for some problems. Key verification. To verify linear time count, the number of transitions the machine performs are relative to the input size. Direct read. If the machine processes each symbol in constant time, scanning the tape in one pass without needing to revisit symbols, it can run in big O of n time. Avoid excessive moves. Here, if the machine frequently moves back and forth along the tape, it could increase the number of steps, leading to the time complexity worse than big O of n. Worst case analysis. Here, check whether the worst case input patterns cause the machine to revisit earlier symbols multiple times, potentially exceeding big O of n steps. State transitions. Ensure that the number of state transitions grow proportionally to n without requiring nonlinear processing per symbol. Simple problems. For straightforward tasks like copying or simple decision problems, one tape machine can often achieve linear time. Complex problems. For more complex computations, the one tape machine may require nonlinear time due to limitations in accessing different parts of the tape efficiently. Simulation. Simulation, the machine on a different input size provides empirical evidence of its time complexity. Head movements. Excessive tape head movements, particularly revisiting portions of the tape, can indicate non-linear time behavior. Function of input size. The number of steps should be linear functions of the input size to confirm big O of n performance. Memory usage. Through irrelevant time complexity, consider how many efficiently the machine uses its single tape for space as well. Optimizations. A one tape machine can be optimized for linear time in specific scenarios such as left to right passing without backtracking. Conclusion. Verifying linear time requires that the machine process each input symbol efficiently without unnecessary revisits or excessive tape movements, ensuring the number of steps grow proportionally to input size.